Good morning, everybody. That was our 1 minute grace period. Hope you're all rocking out. Finale and I are delighted to be back together with you today. And we're going to continue talking about classification, except today we're going to talk about classification from a probabilistic viewpoint. So that's the agenda for today. Let me go ahead and first of all give you some motivation before we get into the technical material. Here is a reminder where we are in the taxonomy of the course. We're still talking about supervised learning. And in particular, we're still talking about classification problems. And if you think about the cube, we're up here now. So move this yellow blob up here to the probabilistic corner of the cube. We're supervised, we're probabilistic. I'm calling this discrete because I'm focusing on the discreteness of the classification problem. But I did want to point out that the features that we think about will both be continuous and discrete. So today we're talking about probabilistic classification. And I wanted to motivate that with a few examples. And I thought a good one to start with, I talked about this right at the start of the semester. This is this thing we've all grown to like, where you kind of swipe with your fingers on a phone and it spells out words for you. And if you think about it, probabilities, that is having the probability of whether you've just swiped out word 1 or word 2 or word 3, having that probability is going to be very important to designing an effective user interface. If instead of looking for a probability and only returning the words when you are confident enough with your prediction of the class, you simply are always using a classification approach that is always willing to return a class, then it's going to be providing words as soon as you start swiping anything. And you can see that that would not provide a very good user experience. To give you some other examples, I want to also try to situate what we're doing in the context of decision making. So far we've been talking about this picture here, where we're training, and then in the yellow flow, we're using our learning system to now make predictions about the probabilities of classes. In the swipe example, the classes were the different words. And this is feeding into a decision problem. Oftentimes when we're thinking about artificial intelligence and we're thinking about using machine learning, we're ultimately interested in making decisions. One example of a decision we might be interested in is this email spam email or not? Here's an example of an email. I think if you read this email, you probably say, yep, that's spam email. You're looking for things like earn a degree without tests. You're looking at these exclamation marks. You're looking at these capitals at the bottom. So think about these as all features corresponding to the words in the email that might lead you to classify this email as being in this case, a spam email that should not be delivered. But again, probabilities are important here. You don't want to be making mistakes when you're delivering emails. There are some emails you get, like an email from your best friend or from your professor in your class, that you don't want to miss. And there are other emails you'd rather not get. It's going to snow again in Boston today, those of you in the Boston area. And I've noticed that the city of Cambridge is not very good about deciding when to have a snow emergency parking ban. So it seems to me that they don't have a very good method to understand the probability with which there will be more than 5 inches of snow. As far as I know, they have not yet announced the parking ban for today. Another example is internet advertising, where you're typically interested in trying to get at the predicted click-through rate on an ad. So this is a probability. It's the probability that a user will click on an ad. And you're multiplying that by the cost per click, the amount the advertiser has bid per click, and the product of these two things is kind of giving you an equivalent bid. And so here, probabilities are very important to be able to get to bids. Quarantine, or what is the probability that you might be infected with COVID-19? That's something important to think about for deciding whether or not you should be in quarantine. And dating platforms. What is the probability that person one will like person two and vice versa? You know, we don't want to be introducing each other. We don't want to be introducing people on dating platforms if the match is not very good. So what is the probability that we have a good match? And just as a toy example here, again, thinking about data match and thinking about Valentine's Day. You may all think that data match is a new idea, but actually goes back at least to the 1960s, where there was something called Operation Match that asked people to complete a survey. I'm just showing you some of the questions here. So dating someone of my own religion is 1, unimportant, 2, slightly important, 3, moderately important, 4, very important. My date's religious background may be. My college class is, the ideal college class for my date is. Men, I would consider dating a girl whose college class is as low as. And so these are questions that were asked at the time in Operation Match. And these questionnaires were converted into punch cards that were fed into huge computers at Harvard. There were 2 companies that were doing this, Operation Match and Contact. One of them sold questionnaires for $3, one for $4. And they both, as the quote here says, they both aimed to expand the campus dating pool from Wheaton to Wellesley, from Pembroke to Mount Holyoke. All right, so that's a little playful, but hopefully all of these kind of give you a feeling for why getting probabilities associated with classes, rather than just, yes, it is this class, or yes, it is this other class. It's useful. It's useful for driving decisions. Hi, Finale.
Absolutely. Yeah. David and I are both decision people, like in the sense of like our research has to do with how various agents make decisions and make good decisions. And probability is really the language, right? Because you can glue so many things together once you have probabilities. One thing that we're working on now. Absolutely. Yeah. And I think that relates to some work that you're doing as well, David, is like it's important to, probabilities help you model the user as well as your algorithm. So you may have the agent and you may have probabilities that it thinks things are certain classes. And then you also are perhaps interacting with a human, and you may want to have a model of what the human is likely to do. And then again, probabilities help you stitch this together. You know, what's the probability that the human will make a mistake, or the human will take this action? In which case, you know, what's the best action for me to take given the information that I know as an agent?
Yeah, that's a really good example. So Finale and I are both interested in this human in the loop decision making, and in thinking about the complementarity between human decisions and learning systems. And as we think about that, it's very useful to model, as you said, Finale, kind of, if the machine proposes this information or makes this recommendation, what is the probability that the user will then do, you know, this thing, like order a test for the patient or do something completely different? And to have those probabilistic models is useful for being able to compose learning systems with decisions. Hi.
Absolutely.
Awesome. So let's dive in. I want to now talk about some of the technical material for today. And as I said, we're talking about probabilistic classification. And I just want to recall, as we get started here, that last week what we were doing was we were doing this. We were saying that the predicted class, for example, n, is one if the discriminant is positive and is -1 otherwise. That's what we did last week. And you remember that we trained this via the hinge loss. I remember the picture for the hinge loss on a negative example is like this. That's kind of what we did on Thursday of last week. And I got very excited about the hinge loss. So today the question is, but what if we like a probability that an example is positive? That's the question for today. I already talked about the decisions that this can drive. We can get to a probability, we can classify spam, we can rank adverts, we can make decisions about medication, we can decide on snowbands, etc. And we're going to talk about two approaches. Approach one we'll call discriminative. And approach two we'll call generative. Discriminative or generative. In both cases, we're going to be using maximum likelihood estimation. And we'll see as we work through class today, we'll understand what maximum likelihood estimation is all about. And we already saw that, of course, about a week ago as well, when we talked about probabilistic viewpoints on regression problems. And today we're doing probabilistic viewpoints on classification problems. So the discriminative approach will work as follows. We'll be finding parameters W that maximize the conditional probability of the labels in the data. So this is what we would call conditional likelihood. So what did I write down? I said, think about providing a probabilistic model for how the label of example N depends on, is conditioned on, the features of example N. And W here will be the parameters of the probabilistic model. And this is the product symbol. And we take the product because we think about each of our examples in our data as being independent of each other. So read this whole thing as the conditional probability of the labels in your data, conditioned on the features in your data. This is going to be approach one. Approach two we'll go ahead and write down the joint distribution xn, yn. So this is now the joint distribution on example, on the features in an example and the label associated with an example. So we'll just call this the joint likelihood. And let me just write that again a little clearer in case you can't read where the comma is and all of that. This is this. We'll call that the joint likelihood. So we're thinking about the features being jointly distributed with, presumably with some correlation with the label. If there's no correlation, we wouldn't be able to predict the label. So this approach we'll think about as being a simple approach. This approach we'll think about as being a flexible approach. It allows us to add the knowledge that we might have about the way the data is generated, which is why we'll think about it as a generative approach. And we'll also see in our concept check that it can handle missing labels and also kind of missing features quite elegantly. Yeah, Charu, that's right. So you can literally think about this as being kind of how is the data, the XY pairs, generated? And I'm writing conditioned on the parameters. So I'm thinking we set the parameters of some probabilistic model, and then we push a button, and the model spits out an X and a Y. Push it again, the model spits out an X and a Y. That's what I mean by generative. And the particular methods that we'll get to, here we'll get to logistic regression. Despite its name, it's a classification method. Okay, don't be confused by the name. And here we'll get to both kind of a multivariate Gaussian approach and we'll get to an algorithm called naive Bayes, a machine learning method called naive Bayes. Now, I just want to make a couple of notes. One, it will be convenient today to adopt 0, 1 for our binary classes rather than -1 + 1. You'll see why. And if you want to think about how we would use these types of probabilistic models to classify a new example, I want you to think about it like this. We would say that a new example is 1 if the probability of 1 conditioned on features X is greater than the probability of 0 conditioned on features X and 0 otherwise. So if this is what we're doing, we immediately have this conditional probability. If this is what we're doing, we're going to have to work with the joint distribution to figure out either this conditional probability or something proportional to that conditional probability. But that's how we'll be classifying. What I'm saying is we'll classify according to the class with the highest probability given the model that we estimate from the data. Right. So this will, I think, make sense as we begin to work. Any questions so far? Okay. So let me talk about this discriminative approach first. Logistic regression. The idea is, here's the idea. We'll model P, Y given X through a sigmoid, also called a logistic function. And what is that? That's this. Probability Y = 1 given X is given by (1/1 + e raised to the power of the score, this same linear interaction we've been using for a while now between the parameters of the model and the features of an example. Let me show you what that logistic, this is called a logistic function. Logistic function looks like this. I'm not going to write down the W0s anymore. Let's pretend the W0s have been absorbed into the rest of the weight vector. using the trick we've talked about before. And we'll write the sigmoids using the sigma notation. So it's a function of a scalar. The scalar is the quantity that we negate and then put into this value that we raise the exponent to. Important thing to notice about the sigmoid function, one, it takes numbers from minus infinity to plus infinity, and it squashes them to between 0 and 1. That's good because that gives us a probability. For the input 0, we cross the axis at 0.5. So this value here is 0.5. And 2, this is a nicely differentiable function. That will be helpful as well. Also, just to point out that if I was asking you for the probability of y equals 0, then I would just take 1 minus this, and the curve would kind of look like that. So that's my probability of y equals 0, which is 1 minus my probability of y equal 1. And by symmetry, you can see that I'm going to be able to get that by essentially negating this value. I'll use that in a second. So to work with this, we'll write shorthand H equal W transpose X. And then, as I said, let's just note that this means that we can write probability classes 1 given X as 1 over 1 plus E to the minus H, and probability classes 0 given X turns out to be 1 over 1 plus E to the H. So just without the negation. And you can show that algebraically just by working with 1 minus this quantity, or you can kind of see that by symmetry, I want to negate this, and then I would get this function here. So this is the sigmoid function. This is our model for the probability of a class conditioned on a feature vector describing my input. And then there's a trick. This is where we use this idea that y is 0 or 1. So since y is 0 or 1, we can write p y given x. Now, both for y equal 1 or y equal 0, can just write a single expression, which is p y equal 1 given x raised to the power y multiplied by p y equals 0 given x raised to the power 1 minus y. So stare at that for a second. When y is 1, this term goes away, and we're just left with this term. And when y is 0, this term goes away, and we're just left with this term. So this is just an expression for, it's a convenient expression for the probability of a label given a feature vector x. So now we have all of that. We're going to use this maximum likelihood estimation approach, MLE. So we're going to be looking for parameters of this model that make the observed classes as likely as possible. That's what we mean by maximum likelihood estimation. And to do that, we'll take as our loss the negative log likelihood. Because we're used to minimizing loss, so minimizing negative log likelihood will be the same as maximizing log likelihood. And I can take logs because it's a monotone transform of my probabilities. So I'm going to write down the following loss function. When I take the log of the product on the data and negate, I get a summation, and this expression. So remember I had this product here. So I'm taking the log of this, so I get a summation, and I'm negating. And I can now write this out just by substituting in this expression. And when I take the log of this expression, this product will factor out into sums, and these exponents will come down in front of my log terms. So I'm going to get this. And I'm also going to substitute my sigma expression for my probabilities. So here, remember, I'm using the shorthand X to denote the inner product between the parameters and the input vector. And remember, for a prediction of y equal 1, it's the sigmoid applied to minus that value. And for a probability of y equals 0, it's the sigmoid applied to the positive value. And h sub n is just this value for example n. That's my notation. So nothing complicated has happened here. This is all algebraic. This is now an expression for the negated log likelihood. And then the last thing I'm going to do is I'm going to recognize that my sigmoid function is 1 over something. So when I take the log of 1 over something, I get the negation of the denominator. So I can now just go ahead and write this as this. Okay. So it's just algebra, but it gets us to an extremely interesting place. Here's where this gets us to. Now we can think about this as the loss. Think about this as the, actually this term over here. Think about this as the loss on a negative example. This log to the 1 plus e to the hn, that's the loss on a negative example. That's exactly what we've written down, the loss function. And so we can draw a picture of what that loss looks like. So, and again, this is for a negative example. And this connects what we've just done with what we did on Thursday of last week. Remember we had our 0, 1 loss function that looked like this. And then we added onto this our hinge loss, which looks like this. If you plot this function, this log of 1 plus e to weight transpose x, this is just a function of weight transpose x, you get this function. It crosses the line around here. It's about here at -1, and at 1, it's up at 1.3. You get this function. This is called the logistic loss function. So this is really cool. Let's notice what happens. I started with a sigmoid function to describe the model that I was working with. And then when I pushed maximum likelihood estimation through the likelihood that corresponds to this model, my loss function has a loss term that we can draw like this. And what you notice is that it's differentiable and convex. So that's good. That means we can use gradient descent methods to minimize this loss, which would be fitting the parameters of our model. And you also notice that unlike the hinge function, it still penalizes our predictions when we're making, as we get closer to the decision boundary. So it prefers to make better decisions on correct predictions. And if you somehow think about classifying this negative example as being negative when we're to the left, it's still trying to push away from that decision boundary. Any questions about what just happened? There's one other thing that I can tell you, which is also really neat, which is that now we can actually think about stochastic gradient descent. Not actually going to take the derivative for you, but you can take the derivative of the loss to figure out the gradient vector. What I do want to share, what I do just want to tell you is that if you work with this loss function and take the gradient and do stochastic gradient descent, and we can think about a positive example, and we can think about a negative example. First of all, you remember that when we were working with the hinge loss, the algorithm we ended up with for training our model was if the prediction is wrong, then update your parameters by adding the step size eta multiplied by the feature vector corresponding to the example. And similarly for negative examples, if the decision is wrong, then we subtract the step size multiplied by the decision, the feature vector. And I showed you this in the animation at the end of last class for the special case of the perceptron algorithm where eta is equal to 1. And if you take the gradient of the logistic loss function, this loss here, then this is what you get. For a positive example, you get that expression. And for a negative example, you get this expression. And these look very similar. See how, imagine that on your positive example, you're actually doing very well. So the probability of it being associated with a label 0 is very small. That means you don't move the weights very much. If you're doing very badly, the probability associated with it being 0 might be high, in which case you move the weights quite a lot. So it's very much like this, where here we move them if we're making a mistake. Here it's a smoother adjustment based on how well we're doing with regard to the correct class label. And also you notice here that the algorithm continues to move the weights even when the probability, according to the current model of the label being 0, is smaller than 0.5. So even when we're currently classifying correctly, the algorithm continues to move the weight vector, kind of moving the boundaries to continue to improve them. And kind of what I want you to think about here is that algorithms come from loss functions. You take your loss function, you take this idea of stochastic gradient descent, and you get an algorithm for training your machine learning method. And we've seen that here by pushing through this probabilistic approach for binary classification. Okay. Any questions on this?
Charu asked a question in the chat, which is, why are we moving in the direction of the gradient for the positive examples?
Why are we moving the gradient for positive examples? Yeah, so the basic update is that you walk against the gradient. So all of these are derived by the basic expression where you take the current weight vector and because we're going downhill, you want to do this. This is our basic SGD step. And it just turns out that when you take the derivatives, you get a negation coming in. And I think we derived that last class, and that's how this becomes positive. And the same type of thing here, when you take the derivatives, the negation cancels out with this negation. So it's algebraically the right thing to do when you take the derivatives correctly. Okay, great question. Yeah, and then Alec asks, if it's differentiable and convex, why not find an analytical solution? So when we were doing linear regression, we were able to invert matrices and find out an analytical solution. In this case, you're not able to just directly find an analytical solution. These are not quite so well specified problems. So we're still going to have to follow gradients to solve the problem. So we're going to take a little break in a second, but I do just want to preview the generative approach. That was the discriminative approach. In the generative approach, what we're going to do is we're going to model this joint distribution directly. And we're going to need to do three things to do this. One, we'll need to decide on a generating process. Two, we'll need to parameterize our model. And three, we will then minimize the negative log likelihood. And what we're going to do in particular is we're going to use the chain rule, sometimes also called the product rule, from probability. And we're going to write P of xy as P of x given y times the marginal probability of y. So hopefully you've seen things like this before. This is called the chain rule from probability theory. This is going to be useful because now we can model each of these pieces separately. And if you want, you can also think about this generatively, where you pick a y according to a distribution on y, and we'll call this the class prior distribution. And then conditioned on having picked a y, you pick an x. So we'll call this the class conditional distribution. And we're going to need to model both of these. This one will be pretty simple. We'll model it for the binary case as a Bernoulli distribution. This one, if it's continuous, If the x's are continuous, then we'll be using Gaussians. If the x's are discrete, then we'll be using what we'll call naive Bayes. I think the last thing I'll tell you before we take a break is how will MLE actually look, maximum likelihood estimation. So now you're looking for parameters that maximize the joint probability of the data. And because we've used the chain rule, we can write this like this. Okay, the product of those two things. And because logs play nicely with products, we can write this whole thing as, and then I'm also going to take the negation, the argmin of minus the sum of the log of p xn given yn. That's using the first thing here, taking the logs, and I'm negating minus the sum of the logs of the second term. And the nice thing about this is that you can now kind of optimize each one of these separately. So this one, you'll solve for some parameters W star of your class conditional. And this one, you'll solve for parameters W star of your class prior. Because the parameters for this distribution only appear here. I'm not writing the parameters explicitly here. I hope that's not confusing you. So it's implicitly parameterized by parameters. And the parameters for this part of the distribution only appear here. So I can kind of separately solve these two optimization problems. And we will generally, in this case, be able to get at that analytically, okay, when we solve. So I think this is a good moment to pop out. We'll just take a couple of minutes. You can feel free to go find a friend if you would like to. And we'll start again in 2 minutes. And yeah, I'm happy to take questions while we take a little pause as well. So Justine, go ahead, please.
Yeah, I'm just wondering, for the last thing you explained about maximum likelihood estimation for the generative approach, am I understanding correctly that when you say we maximize the joint density, it's equivalent to maximizing the probability of y knowing x, because it would just mean that we divide by p of x, which is a constant? Like, I would have thought that we would have wanted to maximize p of y knowing x, and then in the computation is like p of x knowing y times p of y, which is what you wrote, divided by p of x. And so this p of x is a constant, and so it's equivalent? Yeah,
not quite. So I didn't tell you yet how you can use this to classify a new example. Right now, what I want you to understand is that we're going to try to fit, so we're being much more ambitious now. We're going to try to understand both the x distribution and the y distribution.
Okay.
And in fact, we're going to try to understand like the way they interact with each other. And that's all I've said so far. I've said, let's try to write down that joint distribution. And I used the chain rule to factor it into 2 pieces. That just turns out to be useful. You're asking me, I think, how you would use this to classify a point. And we would use this to classify a point by using Bayes' rule, which I think is where you're going.
Okay.
So we'll see that in a second.
Okay, thank you. It was just to be sure.
Yep, good question. And let's take Charu's question and then we'll get back into the flow. Go ahead, Charu.
Yeah, so you mentioned that we're solving separately for W star of the class conditional and for the W star of the class prior. So we're
Yep.
going to get two different values of W star. So which one are we actually going to use? Are we solving for the difference in the two W stars?
Yeah, sorry. I should be more careful with notation. So this is just think about this as being kind of the W star corresponding to this distribution, and these are different parameters. So it's not like they're the same parameters. Let me maybe write it as, yeah, sorry, I confused you. Call this maybe W, the parameters for the class conditional distribution, and call these the parameters for the class prior distribution. They're different parameters. They parameterize respectively this part of the distribution and this part of the distribution. Does that make sense
Okay.
now? Sorry for confusing.
Yeah, that makes sense. So then like our ultimate W that we're solving for, it's based on those two. So that's also separate from those two W's.
Yeah. Think
Okay.
about the W we actually care about as the combination of
Mhm.
all of the parameters. That's right.
Okay, thank you.
Melissa?
Yeah, I was wondering why the joint distribution was split up into P of X given Y times P of Y as opposed to like P of Y given X times P of X. I was wondering like, I guess what the reason was there.
Yeah. It's a choice. You could do it other ways round. It turns out that we'll realize I think this is quite natural. It's quite natural to think about the class conditional data distribution. Kind of think about it like, remember I keep talking about cats and dogs. So think about this as if I tell you you have a cat, what does the distribution on the features of the cat look like? And that turns out to be quite easy to think about. Okay. Whereas if you flipped it, if I said, here are some features X, what does the distribution on Y look like? That's going to be more complicated to think about. So this is just like a natural way to decompose things. And we can choose to do it whichever way we want. And that's what I meant by number one, decide on a generating process. And this is something that when you're in the practice of using probabilistic modeling and machine learning, you get very used to thinking about the sensible way to do that. So you get a nice clean model. Finale's an expert on that. And I see she's chatting away in the chat. Okay, thanks for your question. All right. And so just on the question that we had a minute ago, how do I classify? Here's how I classify. So just as an aside, I classify via Bayes' rule. So what I just need to notice is that this, which is what I care about for classification, is proportional by Bayes' rule to this. And we have these terms directly in the model that we're trying to estimate. So that's how we'll classify. All right. So I want to first of all just talk about the class prior. That was this part of the model. And remember I said that we're just going to model this as Bernoulli. Random variable with probability theta. And so we can write it as Py is this expression using the same trick I described earlier. Remember, y is 0 or 1. And then I won't derive it for you, but it's relatively easy to derive. And you can check by taking the derivative. So now kind of think about taking d loss d theta and setting that to 0. If you do that, it's just a couple of lines of algebra. You should take the log to make it easy. Then you can show that the parameter you would estimate theta is the sum of the y's divided by the number of examples in your data set. I think that makes sense. So it says that if a quarter of your examples are ones and 3/4 are zeros, then your maximum likelihood estimate of the parameter theta of the class prior would be 0.25. So that's the class prior. Now, we have to work harder to get at the class conditionals. So let me first of all do the continuous case. So remember, we're interested in modeling this. And here I want you to think about the x's as being continuous. And we're setting this up so the x's have to be either continuous or discrete. You can do more general things as well, but just to set our thinking. And in particular, the way we'll think about this is we'll think about the x's for class 0 as being normally distributed with a mean vector and a covariance matrix for class 0. And we'll think about the x's for class 1 as being normally distributed with a mean vector and a covariance matrix for class 1. So the parameters of the model, the parameters of this part of my model are these. And then remember, you also have the theta parameter of the class prior. And taken all together, those are the parameters that we're interested in. And not going to get into the details as to how you derive the maximum likelihood estimate of these parameters. You actually will do that in the problem set that's out at the moment. But what I do want to point out intuition I want to give you is that the data, you should kind of think about the data as being in two piles. So the MLE problem separates by class. What do I mean? I mean for class 0, use the following data. Use all of the x's that have yn 0. And then from that, estimate the mean and the covariance. So kind of picture, if you can, just think about 2 dimensions and picture a 2-dimensional feature vector and picture it being distributed according to a Gaussian distribution with a mean and a covariance. Covariance might stretch it in a particular direction. And that's like I was saying, think about yn0 being cats, think about there being 2 dimensions, like, I don't know, how fluffy are they and how snouty is their face, might be a way to think about cats versus dogs, 2 dimensions. This is trying to capture the descriptions of the cat as a multivariate Gaussian, and you would estimate these parameters. And then you do the same thing for class 1. For class 1, you just use the part of the data that is labeled as 1, and you estimate the parameters. And you'll work through that in the section. And I'll just give you, I mean, it's also very easy to find pretty much anywhere you look. I'll just give you the answer you would get. I'm not going to give you the derivation, but I'll give you the answer you would get. N0 here is the number of examples with y equals 0. So for the mean of the Gaussian component corresponding to the class 0, I'm saying you just take the average of all of the vectors associated with class 0 and divide by the number of examples in that class. That's the MLE estimator that you get by setting the partial derivative to 0 and solving. One thing I will just mention is that you can also understand the decision boundaries. I'll show you a little illustration of that in a second, and you'll work through this in the section material. But it turns out that if the two classes have the same covariance matrix, you get these linear decision boundaries, same covariance, then you get linear decision boundaries. Otherwise, you get quadratic decision boundaries. And let me remind you that here the kind of what is the decision boundary? Remember, we're going to classify as a 1 or a 0, depending on whether py equal 1, px given y equal 1 is greater than py equals 0, px y equals 0. So that's our classifier. And so the decision boundary are all the x's where the ratio between these two is a constant. That's your decision boundary. It's the set of x's where the ratio is a constant. And you can see that just by rearranging this, because this is a constant probability. This is a constant probability. So I'm not going to get into the details of deriving why the decision boundary becomes linear or quadratic, but you'll see it in the section material. Okay, so that was so much about a class conditional model with continuous x's. Let me tell you a little bit about how to think about a class conditional model with discrete x's. And this goes under the name naive Bayes. So now, feature D of our input vector x takes on one of 1 through j discrete values. Our data is now discrete. So if you want to make this concrete, think about hair color. So feature 1 might be hair, and the value of the feature is the color of the hair. And capital J is the number of values the feature can take. So if there are 10 hair colors, then J would be 10. And the key assumption that we're going to make to be able to model this class conditional distribution in a clean way, and this is what is known as the naive Bayes assumption, is that each dimension of x is independent conditions on the class. Let me write that mathematically for you. So it says that px given y equal 1 is the product over the features d of px d given y equal 1. So this is conditional independence, conditioned on the class, I can sample, remember, think about this generatively. I sample hair color independently of eye color, independently of height, independently of leg size. They're all sampled independently, conditioned on class. In this case, y equal 1. We do this to avoid having a lot of parameters in the model. If we did something else, you'd kind of have to have enough parameters to capture the interactions between, say, hair color and eye color, and height, if that was an interaction. You'd have to model it in a more elaborate way, and the number of parameters you would work with would get a lot larger. And I think then the last thing to tell you is, how do we model this? And we model this in the most simple way you could imagine. So for feature XD, we model as a categorical distribution. Categorical generalizes the Bernoulli distribution from binary to more than binary, because this capital J can be larger than 2. So the way to think about this is that if I'm talking about hair color, blonde, black, brown, suppose there are only 3 hair colors, then this is kind of telling me the probability of each hair color, maybe 0.2, 0.5, 0.3. Just the probability associated with each discrete value that the the feature can take. And notation for this is pi sub k d j. So what is this? This is the probability in class K. So far, our classes have just been binary, of feature D taking on value J. And because of our independence assumption, that will completely describe our model. And for this to be a well-defined probability distribution, when you take the sum over those probabilities pi, you better get 1 for all A or D. Okay. There are more details I could give you on this, but I think that I won't get into many more details in the interest of time. What I do want to say is that you can then do, and again, there'll be an opportunity to read about this in the section notes. You can now do a maximum likelihood fit of parameters, which we would typically write as pi 0 and pi 1 for class 0 and class 1. And again, you kind of split the data up into the class 0 data. You use the class 0 data to estimate the parameters for class 0. You use the class 1 data to estimate the parameters for class 1. And it kind of comes down to a pretty simple summation and division exercise to estimate. And we give you the expressions. And the section notes are also in, I think they're not currently in the book, but I'm also going to maybe slightly modify the relevant chapter. You also don't need the details on this for your problem that you'll see in the problem sets this week. Okay, so what did we do? We did the discriminative approach. We did the generative approach. Within the generative approach, we did this continuous version with Gaussians. We did this discrete version with these categorical distributions. Just as a note, the naive Bayes classifier, you may wonder what the decision boundaries look like, has linear decision boundaries. And the intuition is that, again, it's kind of making this independence assumption. And that independence assumption means that you get these simple linear boundaries between classes. I won't derive that for you in the interest of time. And then the second note I want to leave you with is that you can also get to multi-class. And for multi-class, we typically would think about the classes as being capital C 1 through K. So now there are K classes rather than 2 classes. And you can do this generatively. This one is easy as a generalization of what we've done so far. You just use a categorical class prior. Not Bernoulli. Because now there's more than 2 classes, and then you estimate class conditionals for each class, just like we did, because everything was already breaking up over the different classes. So there's no new complication. And how would you classify? You classify as argmax k of the expression we got through Bayes' rule. So that's how we would classify. And then if we're thinking about the discriminative approach, where we had binary classes, and we had one set of parameters. What we would now have is we would have separate parameters WK for each class. And then we would bring the models together. We were using the sigmoid function. Now we would use a softmax function. So again, when we're doing discriminatively, this is what we're modeling, the label conditional probability. And we'll write this now as what's called a softmax function, which some of you might have seen before, which for class K looks like this. This is the softmax function. Just look at this function together for a second and make sure you understand why it makes sense. So first of all, you should be able to check that if you were to take the summation of this fraction over all classes, that it would add up to 1, because you'd have the numerator would then be the same as the denominator. The denominator is just adding up over all classes. So it adds up to 1. And then the second thing that you should be able to check is that as the discriminant value for class K gets bigger and bigger and bigger, then that term will come to dominate the denominator. And so you'll get a probability going towards 1 on that class. So that's the sense in which this is a max. And it's a soft max because it's differentiable. We don't put all of the probability on the class that just happens to have a slightly higher discriminant value. And in particular, you can also check that if all the discriminant values were 0, then this would be the uniform distribution. It would put the same uniform probability on each of the classes. And you can train this using maximum likelihood approaches. Okay. So that's a look at some of the math around probabilistic classification. Let me show you just a few examples of this, and then we'll have a little time for a concept check. First of all, this is just a picture to show you the discriminant approach, where here's my data in my original feature space. And just as when we were doing linear regression, we can use a basis transform to move the features into another space. And so what we do here is we transform this 2-dimensional X space into a different 2-dimensional space by introducing a Gaussian basis here, which is this dimension, and introducing another Gaussian basis with mean here. So in the dimension of the first basis, where we have a Gaussian whose mean is here, these blue points have very high probability mass. So they map to these blue points here. These blue points have very low probability mass because they're a long way away from the mean of the Gaussian. So they map here. The red points are in the middle. And in the cases of the second dimension in the basis space, which is given by a Gaussian whose mean is here, the red points have very high probability mass, and the blue points both have low probability mass. And so this becomes linearly separable in the new two-dimensional space. And then this black line is showing you the projection of that back down into the original space. Okay, so again, you can do basis trick with these linear discriminants and still manage to classify data that looks like that. And then in regard to the generative approach, here's a picture of two class conditional Gaussian distributions, the red distribution and the blue distribution. And then this is showing you the probability you would infer for class red versus class blue as you move from the 1, 1 part of the input space to the -1, -1 part of the input space. And as you do that, you initially are very certain that you have a blue example, and in the end, you're very certain you have a red example, and between you're not sure. And you kind of see it here in the picture. Your blue data lives over here, your red data lives over here. And then the last thing I'll show you in this example is suppose we had 3 classes now, rather than 2 classes. And here are 2 input dimensions. And this is showing you the same thing. Now, this is the blue is the probability we're in the blue class. The red is a probability red. The green is probability green. And it's also showing you the decision boundaries. And this is what I meant by these 2 distributions have the same covariance matrices. And this decision boundary is linear. But these pairs of distributions have different covariance matrices, which gives you this quadratic decision boundary. So those of you that, I know we're almost at time, but those of you who still have a few minutes, I do just want to kind of try to quickly do a concept check for those of you that are willing to maybe stick around just 5 minutes more. Here's the concept check. So I give you examples that are initially there are only 3 examples: positive, positive, and minus. And I ask you for 3 different loss functions. Which line or lines would they prefer for each of those loss functions? 0, 1, hinge, logistic. And then I give you some additional unlabeled data. See, these points are not labeled. And I ask you, now thinking generatively, which decision boundary might you now prefer? I ask you to pick one of the decision boundaries. And then I ask you to think about when your decision might change if I give you unlabeled data and you're thinking in this probabilistic generative way. Okay. So I'm going to post the link to that in the chat. And then I'm just going to open up the rooms and we'll just send you there for 3 minutes.